Hey everyone, good afternoon. How is everyone doing? It is 1 p.m. in Knoxville. It is noon in Texas. It looks so bright in here. One of these days I'll get the lighting right. So, how's everyone doing? We can work on some 201, some 320, some 474, whatever people have questions with. We can start working on. I might pull up some 201 here in the background. It's always kind of a good staple of office hours. Hey, what's up, Jessica? Can we do 2B? You bet. You're here first. You get first call. Let me pull up that one right there. You can always feel free when I'm always here kind of watching when the audio is playing. Feel free to drop it in, but you were first. You got it. Let's go talk about that one. I'm pulling up the assignment as we speak. I was getting 201 ready and then I'm hopping over to here. This one is worth 2 grades. This assignment. So this is important. This is a big assignment. Okay, we almost have it up and going. Like 5 seconds right here. Assignment is getting ready. Here we are. Assignment is ready. I'm going to increase font on this a little bit. Oh, got to do that. There we go. Much easier to see now. Cool. I think we're good to... Let me do this. 2 seconds here. Getting everything ready. RMD, RMD. Okay, now we're good to go. Now we are good to go. Let's head over to the main screen and start talking about that assignment. Class is over. Class is not over. So we have right here question 2B, or not 2B. Lame jokes. We need to make a model with all two-way interactions omitting the offending row. Now, this is not part of this one, but we're predicting... Are we doing fuel efficiency? Are we doing fuel efficiency? Hey, what's up? Cool, Nicholas. So good to see you here. Just happy positivity today. That's what we do. We just stay positive. That's what we do. Is this... Let me look at which model we're making right here. We're doing demand. Okay. And there's the offensive row. So the offensive row we learned from looking at is 337. And here's our model. We need to do ex4 bike. And so we load up ex4 bike and we make our model. And we can take a look. We can make a summary of this model right here. And here's a summary of the following model. And you can see we have a lot. Everything is significant in this model. So see, I'm confused because prior you were working with ex4. Yeah, it is ex4 bike. Sorry, I was trying to figure out which data set we were working with and I was looking through. But this is ex4 bike that we're going to be working with right here. So we are working with this data set. The strength of relationship demand might depend on other variables. For example, the strength of demand and average temp may depend on average wind speed. So fit a model with all two-way interactions. So with all two-way interactions, and there's a big thing right here. To get all two-way interactions, I'm going to take this model right here. And this is how to get all two-way interactions. All two-way interactions is going to be the following thing. I'm definitely going to put a note in this video because I think a lot of people are going to ask, how do we do this? Great question. We do the following. We raise it to the second, and that'll fit all two-way interactions. This will be every single two-way interaction right here. So this is all two-way interactions fit to the model without the offensive row. We should call this dot int or something like that for the interactions. This is the new model with all the interaction terms included. So then we want to see if it is statistically significant. Now you'll notice there is actually only one statistically significant interaction. The statistically significant interaction is right there. And is there? Nope, there's only one. It's this one right here is the statistically significant interaction. And I believe we are then going to visualize this. Well, we're not going to visualize that one yet. But we can view this with the C interactions many equal true. So C interactions of our model, many equals true. We need to make this plot bigger right here. And let's remember which one of those is significant. The significant one is, it's going to be average temp, effective average temp is the significant interaction. So a big thing we should know about interactions immediately when we look at these plots. Oh, wrong model. Wrong model. There we go. Got to make these plots really big. Okay. We're going to skim through these really quick, and then we're going to remake them still. Make the font smaller. And make them again. And now we've got a decent looking plot. I'm going to go... Sure. The things are always in the wrong area. I'm going to do one last thing. Let's go here and go loc equals top right. Can I do that? Oh, it destroyed it. the location, is it top right? No. There's different locations you can do. You can put the location as top right, top left. I'm not going to worry about the location then. We're going to go with what we got. Okay. So let's take a look at these plots right here. And we remember that it's average temp, effective average temp, where we have the strongest interaction. It shows us right here the interaction between first average temp and effective average temp. And I'm going to disappear because you'll notice that we have here pretty crisscross lines. If you look at the lines, they're pretty, a stronger interaction. If you want to see a weaker interaction, the weaker interactions are where the lines are more parallel. Those are weaker. Those are weaker. Those look slightly strong, but the only statistics, those are weaker. The more stronger the interaction is, the more stronger. The strongest interactions are going to be the more perpendicular lines. And we see here the strongest interaction, weaker, a lot weaker, very weaker, and just the more perpendicular lines. So kind of as a big review, this is like our big mega review. When you have a very weak interaction, you're going to see lines more like this. This signifies weak. And the stronger it is, so the stronger it is, the more perpendicular it is. Now, it doesn't mean it'll be perfectly perpendicular, but the more perpendicular it is, the stronger it is, and the stronger it is, the lower the p-value. So the stronger it is, the lower the p-value, and let's take a look at those p-values again. The only one we have that is statistically significant, is the interaction between these. Now, that doesn't mean the other lines will be perfectly parallel. The other lines to be perfectly parallel would have to have a p-value of 1. So you do see some, still insignificant. Oh, that's the main effect. You see some insignificant but a little bit lower p-values. The weakest of all are these. These are the weakest interactions. So I think it wants us to take the strongest interaction right here and include that in a model. Let's see what it says. Fit a model predicting demand and average temp and from average temp and average wind speed, including the interaction but omitting the offensive row. Examine the results of summary and visualized model. Is the interaction statistically significant? So we're going to take this code again right here, and we're just going to input a little chunk right here. So we can kind of put some new code, and we're going to only include the variables it wants us to. The variables will be these variables right here. And then it says include the interaction. So we need to include the interaction but omitting the offensive row. There's that. And then we need to include just the interaction. So we have just the interaction, average temp and effective average temp. So let's go down here and just grab this, input it in, and run that. And we have an error in our code because we've included something we shouldn't include. Oh, we have to erase this second. That should fix it. Unexpected. Is there a quote in here I'm missing? Y tilde x, comma. Let's take a look. Oh, there we go. And that's just a graphics error. Error average wind speed not found. There we go. So now we've included a model with all three variables. It wants average temp, average wind speed, and include the interaction. So we have the interaction between those. So you can just see the full model right there. And I should call this like my second model. I don't want to use the same naming convention. And I didn't create it. No, I did. So when we look at our model right here, is everything in it statistically significant? Oh, yeah. These, especially the interaction and also average temp, are very, very, very statistically significant. And we have some really great R squared because we have 38% of the variation explained. And we also have 38.17 after we adjust for the amount of variables in the model. Is this making more sense, Jessica? I kind of went on and I think I did all of it. I think I did 2C also. So I made the next model right here. I looked at it and also examine the summary and the visualized model. Is the interaction statistically significant? Now, we might not be able to visualize this one. Let me double check to make sure I have the right. I think it's not visualizing it. Let me double check to make sure I got the right model. Because I can't visualize those types of models, so I'm a little bit worried. Oh, wait. Oh, okay. I just made a wrong model. I knew something looked weird. We're doing the interaction between these two. Wow, I misread. I was like, something's weird. Okay. We're doing the interaction between those two. So, but also, how is it statistically significant? It's less than 0.5. That is the definition of statistical significance. So, statistical significance is just a p-value less than 0.05. So here average temp is significant, and here average wind speed is not significant, and average temp, average wind speed interaction is not significant. So you just look at the p-value right here. If the p-value is below 0.05, statistical significance. If it's above 0.05, not statistically significant. So when it is statistically significant, that means average temp brings with it new information to the multiple model. When it's not statistically significant, it means that these variables do not bring new information to the multiple model that the other variables are not accounting for. Yeah, I know, right? Below 0.05 statistical significance, like boom, less than 0.05 statistical significance. Just get it right there on your arm, be like, okay, I got it. So we can't, I mean, if someone put tattoos that had notes, I guess you have them at all times. You just get everything tattooed. You need to know on yourself. Just cross here, just be like, well, you can't see that. You gotta be like on your arms. There you go. That's why people get sleeves. So they can, tattoo term right there. They get sleeves so they can memorize everything. Can't be like, oh, I guess you could say cover up your tattoos before the test. If you notice right here, these look very what? These lines look very, very what? When you look at these lines, they look extremely what? Very, very what for these lines. You look at these lines and they look pretty, not perfectly, obviously, but these lines look very, very what for the interaction plot. How do these lines look? I would say these lines look basically this, parallel. And that means a very weak interaction. Now remember, they don't need to be perfectly parallel. And of course, we look at p-values, but the more parallel they are, the weaker the interaction. So when we look at right here, you can see weaker interactions are going to have more parallel lines, and stronger interactions are going to have more perpendicular lines. So the stronger interaction, you know, we don't see here. We see a weaker interaction. I've had a lot of people be like, well, the lines aren't perfectly parallel. Well, for them to be perfectly parallel, you would have to have in your output, you would have to have the coefficient of the interaction be 0, and the coefficient of the interaction is not 0, which would give you a t-statistic of 0, and that'd give you a p-value of 1. And then there would be no change to the slopes of the line. So it's rare that the coefficient's ever 0, but it could be 0 because of our uncertainty in the coefficient, because we think it's about 1.71 with an uncertainty of 2.16, so it could be 0. So since it could be 0, it is not statistically significant. So that's the issue right here, is it's like, well, maybe what we're observing between these differences in the slopes could just be by random chance. Could just be by random chance right there. So yeah, that's my mixer. And so other questions you have, Jessica, feel free to ask about anything else. I'm sure 320 is going to be really happy. We kind of worked through good parts of these problems right here. And please remember that this is the correct model for this one. I did make an incorrect model at first. I've done this question before, but I just read it wrong. I was like, wait, the interaction, maybe I'll update to say the interaction between the two of them and their interaction. Does it say and their interaction? Let me see. Yeah, it's include these and the interaction, because you can't visualize certain things. It just doesn't work to make the visual. I don't know, maybe I'll try to figure out ways with Dr. Petrie to make other visuals, but visuals can get really complicated. So multivariate visuals can get pretty hard to create, because it's like, okay, how do we visualize something in like an 8-dimensional space to make it easy to view? And there's really no good, easy way. Feel free to ask another question. I'm going to pull up some 201, but feel free to ask. There's no 201 asking questions right now, so the floor is open. The floor is open to whoever has a question. It is a free-for-all. Free-for-all. Any question is available. Who will ask a question? Getting everything opened up. Let's go here to my Pearson. For 201, I keep getting the problem wrong. I am not sure what I'm doing wrong. Yeah, which one is this, Shakira? Where do I find the slides and notes for 3A? Sure, well, Shakira puts in the question. Let's go look at 3A. Fit a model predicting tip percentage from bill amount and party size. Include the interaction. Look at the visualized model summary. You'll see the interaction is significant, but party size itself is not. So this one right here, I'm going to drop a big hint. This one right here deals with model hierarchy. I don't know how to spell that word. Say spell it? I spell it. Spell check doesn't even know how to spell it. Hierarchy. Model hierarchy. There we go. Hierarchy. Eh? Nope. I think it's right. So model hierarchy. This deals with model hierarchy, which is not a word. So model hierarchy, I've never learned how to spell. Model hierarchy says that, this is basically the answer right here. Okay, so but do remember this, Jessica. You got it. Model hierarchy is a guideline, not a rule. Model hierarchy is a guideline, not a rule. So kind of go into it. Does it violate model hierarchy? Why does it violate model hierarchy? And remember, you can still, you can do these things. Kind of make sure to write more, but remember, model hierarchy is something you can break. It's just not a good idea. It's like taking a shortcut or doing something you shouldn't do. And you're like, I don't know about that. You're like, I don't know. Let's talk about the waitress problem, and let's walk through the steps right here. Shakir, if you miss by decimals, tell me. Sometimes just the way people carry the decimals can lead to such a small difference. So if you're off by the tiniest bit of percent, just tell me. If you're off by like a hundredths or something, just tell me and we can fix it. Because it's just frustrating when you're off by that little and you're like, oh, I just didn't carry a decimal. I did everything correctly. I know how to do this. So tell me, and I'm pulling up the waitress problem as we talk. Here we are with the waitress problem. Okay. So let's talk through the waitress problem. She knows what... What's up? Everyone loves Calzone Tyrone. Exactly. Calzone Tyrone, how are you doing? We got so many new quotes, Calzone. So good to see you here. So let's see. Let me jump into the chat right here. Calzone Tyrone, awesome to see you as usual. Getting everything ready to go right here. It's always, we've had so many, I love all the random visitors. Like, it's like we build this community of kind of like random people who come to streams, and I love it. I wouldn't have it any other way. First Kahoot we did online, Calzone was there and did exceedingly well. Awesome. Well, yeah, how's everything going up there? Everything going all right? Class is going all right? You might be getting closer to graduating, it sounds like. I mean, you should check out Mubot. Mubot has learned everything. Mubot, that's not a good quote. That's when we couldn't get the Lubridator. One more year? Awesome. Well, good luck with everything. Good luck. It's a lot. I remember when I graduated and went job searching. I had a degree in psychology. Went back to graduate school. And yeah, rest is history. Now I teach. I started teaching in graduate school and I really liked it. I started teaching statistics. I started teaching 201. And then I started teaching more, 320, 474. Now they're looking to have me teach time series. So I teach everything from the intro level courses to the senior level courses. And there maybe I'll start teaching a master's level course one of these days. I don't know. When I get old, I'm almost 40, so my hair's just getting crazy. Calzone. It's just New York got more cases. Some of yours. Oh yeah, dude. I saw that there's an uptick. I saw that you're back in the 2000s. I watch the data every day. Oh, Calzone, that's awesome. I really appreciate that. I really, really appreciate that. You don't got to say that. We're just chill right here. We just do work. We just do work. We chill. If we have office hours, we'd eat candy. But I mean, you've seen me more just now wearing everyday t-shirts. You saw when we started out, I was all professional. And now I'm just like, well, thank you, Calzone. Here, let's Shakira with this one right here. We need to identify key portions of this problem. Kind of one thing you can do whenever you get a problem is immediately start highlighting numbers. Numbers are usually things that are going to play a key role in what we're going to be figuring out right here. We kind of got an easier version. We're lucky right here. The first thing we need to know is the mean tip they have. The mean tip they have is going to be mu. The standard deviation of their tips is going to be sigma. And then we have to know what we're doing right here. We're saying that we know this person makes $9.60 on average for a table. Now, that's awesome. I wish I made that much when I was waiting tables. With a standard deviation of $4.30. And that's the variation. That's like the spread of their tips. When they say like, oh, I got a $10 tip, you're like, oh, that's what we would expect because you've got that much variation in your tips. So they would expect $9.30 with a variation of $4.30 going out with the 68, 95, 99.7. So they could get like a $5 tip or a $15 tip. Those are all well within reason for one tip. But we're not doing one tip right here. We're doing the distribution of 50 tips over a weekend. This is why this is the sampling distribution of the sample mean. And the sampling distribution of the sample mean will be normally distributed with a mean that is the mean and a standard deviation that is sigma over the square root of n. This is for the sampling distribution of the sample mean. Do not confuse this with single observations where it's just this right here. I think that's the mistake people commonly make, is that's for single observations up top, and down here on the bottom is the sampling distribution of the sample mean. So what are we going to do? We're simply going to plug in our numbers right here and solve for the mean, and the mean is the mean. So it's $9.60. The standard deviation of the sampling distribution of the sample mean is going to be $4.30 over the square root of the sample size, which is going to be like 0.60 or something, about that. 0.62, I say. 0.62, let's find out. 0.62. 0.61. Close today. We're going to round it right here, but do not round it when you put it into the applet. Do not round it when you put it into the applet. We need like a blinking screen like wow, 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 wow. Do not round it when you put it into the applet. So let's go grab the applet over here. To go over here, grab the applet to Mr. David M. Lane's website. Bring over the web page. Web page! Where'd you go? Web page gone away. David M. Lane's back. Okay, so we bring over the web page, and we now put in the mean of 9.60, I believe it was, and the standard deviation. That's not the standard deviation. Let's check our numbers. 9.60, and then we have the new standard deviation, and I'm going to go right here and do 9.60. I'm going to put in the new standard deviation again. Please note, do not round when putting into the applet. Do not round when putting into the applet. Carry all your decimals out. It's the best way to make sure you get the answer correct. Do not round. I'm just copy pasting from the computer calculator, and that way we just carry all the decimals we can. It rounded at the end, but I think down to the 100,000s, 10,000s, 100,000s, millionths. So it rounded on the millionths, or about 10 millionths. We're probably good. So now let's see the problem. The problem is asking us, what is the probability she makes at least $500? So to make at least $500, what would your average tip need to be? And I need someone to help me out right here. We're going to wait on 50 tables, and we want to make at least $500. So what would your average tip need to be? Because we're doing the distribution of average tips, not single tips. What average tip would you need to make at least $500? What average tip would you need to make at least $500 on 50 tables? You're going to wait on 50 tables this week and you say, I need to make at least this much per table. Let's see. It's the long wait right here. Yeah, you're right. Nice job, Shakira. You get 1,000 points today. Great job, Shakira. We're going to go 500 divided by, we got rainbow pen. There we go. That's going to equal $10. And so that is the average tip they need to obtain. So we're going to say, what's the probability they make at least $10? And there it is right there. It's 25.53. 25.53. Going to copy like that. And go over here to the web page. And 4 decimals. So there we go. That should be correct. We got it. And then it wants the best 5% of weekends. This is where I see people make a big mistake, is one, you need to go to the next applet. And then they put in 5% right here. And they stop. Now, if you were a waiter or waitress and you made $10.60 on a weekend, how would you feel? I'd feel pretty horrible. I'd be like, wow, that weekend was horrible. I made $10.60. But if your average tip was $10.60, you'd be like, whoa, my average tip was $10.60. That was awesome. That's your best 5% of weekends right there, where your average tip. So they waited on 50 tables, and their average tip was $10.60. 50 tables, $10.60. 530, 530. And there we go. That's, were you able to ace it, Shakira? I hope. It's a tricky problem, but carrying all the decimals is usually where I see the error. And then a lot of times people don't multiply here at the end because they find the best 5% for the average tip, but we don't want the best 5% average tip. We want to turn that back into the amount. I think the way my Pearson also does it is way more confusing if you look at their help me solve this. I've had a bunch of people send me the help me solve this and be like, hey, I'm stuck on this part. And I'm like, they just do it in a really confusing way. I've always felt that way. I'm like, let's just use the real units because we can put it into the applet and solve. We don't got to go to Z tables, and Z tables are so bad. Don't look at Z tables. If you have another one, Shakira, feel free to ask, or if you're stuck on a certain part, feel free to ask. We're here to ace these assignments. Is it making a little more sense? I wish when we're in person, I can just like look and be like, oh, that's where it is. If you want me to work yours right now, Shakira, you can. If you want me to do it, I will do it. Since we're not in person, you're here, you're answering questions. If you tell me your mean, your standard deviation, your sample size, I will work the problem you're working right now. So feel free. I didn't enter the numbers right once I went to the Z table. Yeah, and Z tables are all right to use. The applet, I think, makes it way easier because then you don't have to like look through numbers. You'll get the exact answers from the applet. With the applet, you don't have to worry about using a Z table. You can just enter in the exact numbers and it'll turn out the numbers down here, and then you can just convert them really quickly. So Z tables are all right to use, but this carries all the decimals for you, and so then it'll give you more exact because you can enter in like any number you want and it'll give you the number. So looking good. We'll do some of the confidence interval questions because those are coming up. Those are due tomorrow night. So let's take a look at some confidence intervals. If anyone has any other question, let me know. If anyone has any other question, let me know and we will work those problems. Let's go look at confidence intervals for the mean. Let's go do the homework. How much can we do of the homework? We can probably complete the whole homework today. Put the whole homework in a video. Let's check it out. Oh, I've got this right here. Cool. 3 questions. Psh, we got this. Okay, so right here we have some interpretations of a confidence interval. And so what are we getting? Explain carefully what the confidence interval means. So don't read their interpretations. Don't even read it. I am blank % confident that the true blank is contained in the interval blank to blank. So when you look at this, I am 95% confident that the true mean pulse rate of people's hearts is contained in the interval blank to blank. Now, I did move it around because they didn't use the same order, but I am blank % confident that the true blank is contained in the interval blank to blank. It's the only thing that has it. The interval this to this contains the true mean heart rate 95% of the time. No, it's how confident we are that it's in there. 95% of pulse rates will, the will word, tongue twister. The will word is something we don't say. We would say I'm 95% confident, not it will contain it, but that it could contain it. So that should do that one. What is the margin of error? Margin of error is just half the length of the interval. Let's do a little review of just trying to remember how we draw the margin of error right here. So when we draw the margin of error looks like this. You've got an interval, goes from here to here. And the margin of error is going to be this. That's the plus, margin of error minus. So if you have an interval that goes from like 8 to 20, the margin of error would be what? The margin of error would be 6. And we can figure that out by 20 minus 8 over 2. And I want you to think about what we're doing. We're just taking half the length of the interval. So when you look at this, the margin of error is just half the length of the interval. Another way to figure out the margin of error is to figure out the center of the interval, which would just be adding up the two numbers and dividing by 2, because we're just averaging them. The center of the interval is 14 right here, and we should see that 14 plus 6 is 20, and 14 minus 6 is 8. So if you have the right center for your interval, you should just see the plus or minus is the margin of error, and we've done it. We've shown that we know how to calculate the margin of error. It's just half the length of the interval. The length of the interval is 12, just going from 8 to 20 is 12. So you just go half the length of 12. It's just 12 is the length, and you just go half of it is 6. So hopefully that helps reinforce that the length of the interval, that kind of looks like I'm saying that is 12, but the length of this interval is 12. Let's go right here and go like 12. Like 12 is the length of this interval, and half of it, there we go. 12 is the length of the interval, and half of that length is 6. I've seen a lot of people get stuck on these test questions, be like, how do I get the margin of error without the equations? But we just take half the length of the interval. So let's do it. Let's go here and take the length of the interval, which will just be big number minus small number. And wow, they really like their decimals. They really like their decimals. And half the length. Copy in 1 decimal. Now they don't like their decimals. There we go. That's got it. If the researcher had done a 90% confidence roll, would the margin error be smaller or larger? I always ask that you do this. 68, 95, 99.7. I'm like, oh, come on, who's not doing it here in class? Come on, everybody. Let's just do it. 68, 95, 99.7 when you got 1, 2, or 3 standard deviations. And so what are we talking about here? Why do we need that right now? 68, 95. If you were to go back to 90, what would you do? 90. Do you see 68, 95? And if you go to 90, you'd go in a little bit. So would the margin of error be smaller or larger or be the same? 95, 90. The margin of error would be smaller. So the margin of error is going to be smaller. We can also confirm this with Mr. David M. Lane by looking at the Z or the T score. If you were to go to a 95% confidence interval, it works the same way with Z's and T's, even though we'll be using T's in this chapter. Here's what a 95 looks like. There's what a 90 looks like. So 90, 95, 90. 90 is going to be further in, just like 68 is 1, 95 is 2 standard deviations, and 99.7 is 3. Just in case you're wondering, it is technically 95.449 is 2 standard deviations, and 68.23 is 1 standard deviation. So don't worry, those are the exact 68, 95, 99.7 are estimates, but that's why we keep saying 68 is 1, 95 is basically 2, and 99.7 is 3, just going out more and more standard deviations. That goes to the 3rd standard deviation. And so let's make a 95% confidence roll. Now we have to be careful. This is where we learn about Mr. T. I'm sure he's a super nice guy, but we always say Mr. T is mean. Super nice guy. Done a lot of awesome things. We love Mr. T. But why is Mr. T mean? Is because when we're doing T intervals, we're going to use the mean. Or when using the mean, we're going to do T intervals. So, or Mr. T is not mean. So, Eric, start saying that. That's much nicer to say about Mr. T. Mr. T is not mean, but it's for the mean. We use it for the mean. So, right here, he's mean if you do drugs, though. He won't be nice to you. Just watch those 80s commercials. He's not happy with the people using drugs, especially your kid, you're on drugs, trying to sell drugs to kids. Ooh, Mr. T is not, that's where he's really Mr. T. Anyway, it's not about Mr. T. A nutrition laboratory test 60. So let's go ahead and copy this and start taking notes on it. We don't need that stuff yet. So let's go ahead. We're going to start marking this and making sure we know what the notation is, because that's going to help us solve the problem. Let's hop here and let's do it. A nutrition laboratory tests 60 hot dogs, and the mean sodium content is 301 with a standard deviation of 37. Immediately mark your notation. Does anyone watching know any of the notation? See if you can practice right now. Do you know any? I'm going to give it a second right now. Does anyone know any of the notation? This is Know Your Notation with Brian Stevens. Who knows any notation? Let's see. No one knows. So this notation right here, we have 60 reduced fat hot dogs are being tested. That's going to be the sample size. They have to be careful. They find a mean for these hot dogs. So this is the sample mean. They find a standard deviation for these hot dogs. This is the sample standard deviation. Now we have everything we need to create our interval right here, except for the degrees of freedom. The degrees of freedom are n minus 1. And now we need to get the t statistic. And so the degrees of freedom are going to be equal to 59. And the t with 59 degrees of freedom, which tells us which t we are using, probably going to be about 1.98. Let's go find it. We need to go over to statdistributions.com. So let's go over there. Stat distributions, t. Here we go. Drop this in the chat. So we need to make a 59 degrees of freedom. And there it is, 2.01. I should have known that. I think this was 60 degrees from its 2. Yeah, I should have known that. I should have said it's basically 2. 2.001, and that is a 95% confidence interval. If you're wondering, you can do the inner 95% and still get the same answer. You can do the 5% outside or 95% inside. And so this right here is the t statistic, 2.001. And we're basically there. That's pretty much got it. Because from here on out, we are going to just do the equation. It might not have asked us to do it already, but I'm going to go ahead and do y bar plus or minus the t with n minus 1 degrees of freedom, which is what we wrote right there. And then we're going to do times s over square root of n. Brain stopped for a moment there. Now let's go ahead and plug in the numbers. We have a mean of 301. We have the plus or minus for the margin of error, 2.001. And then s is 37 over square root of 60. So we've got all of our notation, which is really where it all hinges on. If you know the notation, you get the formula, you can solve the problem. And let's just check our work right here, because this is the full interval. We're going to mark the margin of error after we solve it. So let's go here, 60 square root, got it. 37 divided by that, got it. Times 2.001, basically doubling it, got it. 9.56. It's 9.56, right? I think so. 301 plus or minus 9.56. Was it 9 or 95? 9.56. That's got it. And so I think that should do it. We just solved the whole interval right here. The margin of error is 9.56. There's lots of ways to ask these problems. And it wants the 95% confidence interval, round to 1 decimal. So 9.56. So 310, 9.5. So it's going to round to, oh, this is subtract. Let's turn off our brains for a moment. 310, 301 minus it. There we go, 294, 2914. And then let's go right here and do 301 plus it. There we go, 310.5. It's going to round to 310.6. There we go. Oh no, what did I do wrong? 37, someone's got a catcher here. No one to watch. We got it wrong. Oh no. Let's see right here. We did something wrong. Let's check our math. Let's check the math. Okay, let's go back here and do square root of 60. 7 point, there we go. 37 divided by, that's that, times it by 2. Is it because we, so 301. Okay, let's check. Are we off by like the smallest decimal? I didn't copy it. Ooh. Okay. So let's check the formula. Ready? 60 square root. Got it. And 37 divided by. Got it. Times 2.001. Got it. That's the margin of error. 3.01 plus this. That's 310.6, 1 decimal, and 301, that's going to make a mistake. 301 minus 2914. What did I copy wrong? I'm going to have to see what the answer is in a second. 60, am I doing square root of 60? Let's see. Did I do 59 degrees of freedom on the T? 59 degrees of freedom on the T. Is it 95% confidence? It's 95% confidence. You know what I'm going to do? I'm going to do it the easy way. Let's do it the easy way and check our work, because we can go right here and we should be able to just write it into R really quickly. Let's go and do, here's the mean of 301, and we want the T statistic, so we want QT with There we go. 0.025 and degrees of freedom 59. There it is right there. That's perfectly fine. It is 2.001. We confirm that. So that's our T statistic right here. And then, oh, it's saved. We don't want that. T stat. It's called T stat. Then we have here the sample size is 60. And then we have here the standard deviation is 37. And so let's take a look. We're going to go ahead and solve for the margin of error. The margin of error is the T stat times, we have here the sample standard deviation over the square root of n. And what is the margin of error? That's what I got, wasn't it? It's starting to look confusing right here. And then we're going to go to the mean plus concatenate minus the, well, we want to do the first one first. The margin of error here, and then the minus the margin of error. And what does it not like? Argument is binary. Look at this. Margin of error is that. So plus, let's just go binary operator. Is the mean currently? Oh, haha. So, oh, I think it doesn't want me to save on the function. Oh my gosh, that's the issue. Okay. One error. That's all it takes in code. What is, oh, and then I've got this right here. There we go. Okay, 291.44, 310.6. 291.4. Am I making a typo? So margin error standard deviation of square root of n, right? Mm-hmm. Charlie, am I not doing something? Margin of error equals the original standard deviation. The standard deviation is 37. And my brain just... Standard deviation of a square root of n, the t-stat. Yeah, I know. That's... I'm wondering, I've seen my Pearson have an error every once in a blue moon. And 301, that's the mean. Standard deviation is 37. Sample size is 60. There's the degrees. I could save the degrees of freedom. The degrees of freedom is n minus 1. We should put that in order right here. So there's the degrees of freedom is n minus 1. So let's put degrees of freedom there. T-stat is what we calculated before. It says 1 decimal, right? I'm really interested. Round to 1 decimal. 37. Y bar plus or minus. Can I find the margin of error if I don't have a sample size? Are you doing the original one? Margin of error will be half the length of the interval. You might be doing that problem where the margin of error is half the length of the interval. So we were talking about that earlier, where if you have the interval and you know the upper and lower bounds, then you can find the margin of error. We were doing that problem. And yeah, no worries. We'll see what my problem says. Whoa, what's going on right here? Do you see this? Clip this. What in the world? Where? Oh my gosh, no. I put a comma. Do you see it? It's that. It was right. That's partially correct. Well, we should have told me that to start. Should have said you have a comma. I know, right? I was like, I do not know what's wrong. I was like, I have no idea what I've calculated here wrong. I'm like, everything seems correct. I was like, this is astounding to me. Please tell me if that happens to you. You know what's really cool about this problem, though? We assume that they're independent, random. We want to assume that they're random. The distribution population is not biased. The normal's the thing we have to assume. There we go. We want to assume they're normal. Is the randomization? We don't know, but if is reasonable to think they are. I think that's on. Yeah. I hate some of these questions. Is the 10% condition met? Yes, these 10% of less, they're less than 10% of all hot dogs. Speed running the rest of these. Is the nearly normal condition met? 60 is kind of large enough. We don't know the original shape of the distribution. It's more than 40, so it's probably okay to proceed because it's a slightly large enough sample size. We don't know the shape of the distribution, but it's pretty large sample. Clearly explain, I am blank % confident that the true mean sodium content of my hot dogs is contained in the interval blank to blank. This question just made me mad. Because you know what we're going to do? We're going to go back and answer this question easily now that we have a cheat for it. 314, 3650. 314, 3650. So 314, 50, 36. And there we go. Let's put the problem on the screen. Now that we got our cheat for it, it's like, just write a code for it, and then you can just put in the numbers. Okay, problem. That's the way you're going to be, right? Did I put another comma? Check. 409. Oh my gosh. Oh, that's way off. What? Oh, I put definitely in the wrong. Oh my gosh. Okay, problem. You win. I can't copy the numbers. You're right. It's 36. I should have looked at the interval and realized how crazy the interval was. So the interval was way crazy because I made a typo on the thing. Okay, problem. Be that way. This is our fun for the day with the problem. 303.8. Brian doesn't know how to copy. He can write the code. He just can't copy numbers into it. That's the moral of the day. There you go. There you go. Confidence interval is y bar plus or minus t n minus 1 degrees of freedom. Not margin of error. Not margin of error. Let me I'll write the formula again. The confidence interval for the t, we have it right here. This whole thing, let me do it on one page, make it really clear. Okay. So the confidence interval for the mean is the following. It's y bar, which is the sample mean, which is your estimate. This is the center of the interval, plus or minus. And then we have, hey, what's up, Nick? Good to see you here. T with n minus 1 degrees of freedom. This gives you the confidence level. S over square root of n. So this right here is the margin of error. So everything right here is the margin of error. Does that make sense, Charlie? That whole portion, the plus or minus, is the margin of error. The t part of it right here is your confidence. So that directly relates to your confidence level. And then this portion right here is your standard error of y bar. So the standard error of y bar is the third part of it. And the second part of it is your level of confidence. And then the bottom thing right here are your degrees of freedom, which tell you which t you're using. That's the degrees of freedom. Does that make sense, Charlie, what the kind of everything right here is? This is your estimate. So sample estimate. It's not the estimate of the sample. It's the estimate we obtained from the sample. So the second part of the margin error is it's the standard error, which is basically a weighted standard deviation for the sample size. So we kind of take the standard deviation and weight it by the sample size, which makes it smaller, which is the central limit theorem. The larger the sample size. Also, we use a p-value of 0.05 in the t-applet? Depends on what you're calculating. I was using 0.05 for a moment. We'll show that again right here. The reason I was using 0.05 is because I was calculating a what confidence interval. I'm going to go here to the two tails. And why am I using 0.05? You can use 0.05 in this one. It works. Because what percent of area is on the inside now? This depends on your question too. What percent of area is on the inside if 0.05 is on the outside? 95% confidence, exactly. So you can change it and use the following right here. That might make more sense because now we're literally shading the inside. But there's weird things you can do. You could do that. Is this still the t-statistic for a 95% confidence interval? Is this still the t-statistic for a 95% confidence interval when I do this? Is this still the right answer? Yes, because 0.025 would be on either side of it. So it can get a little confusing how you can use the applet, because you could even do ridiculous stuff. Like I would never do it this way. But you could do this right here, and that's still the same t-statistic for a 95% confidence interval. The best way to use it, in my opinion, is to use this and just put 95, and then you've shaded the middle 95. The second best way is probably to just do the outside and do this. So what kind of confidence interval do we have here, Charlie? This is a what? I know, that's just weird the other way. What percent confidence would this interval be? This is a what percent confidence interval the way this t-statistic is calculated? 98, exactly, because it's the inner portion that matters. Yep. So, and once again, it's 10 times easier if you just go here and put 98 and do it that way. Same number, just calculated different ways. And so, yeah, great work right there. Not today, my Pearson. We didn't say this, the famous saying, not today. So we assume that they have to be normal, normal condition. And we're going to assume that they are random. It didn't say. We do not violate the 10% condition because they're less than 10%. And and we don't know if it's satisfied. We'll just take a good guess because 50 is more than 40, and it would have to be really skewed. And then we are 95% confident that the true mean sodium content of these hot dogs is contained in the interval blank to blank. There we go. This last one's not so bad because we're given the sample statistics to start, and it literally labels them for us. We don't even got to care about this hurricane stuff. We're just solving a math problem right now. So here is our notation, and we're just talking about will your flight get to its destination on time? To the right are our histogram and summary statistics for the percent of delayed arrivals each month. Consider these data to be a representative sample of months, which means they're pretty random. There is no evidence of a time trend. The correlation was very low for the time trend. Okay, so they're saying it's not a time series problem. They're doing that for all stats, people being like, hey, it's not a time series problem. Don't worry about the time order trend. Okay, so from here, it probably wants us to calculate an interval after it asks a few questions. The conditions are going to be that we have less than 10% of all flights are selected. 72 sounds like less than 10% of all flights are selected. So we should not check this box because it does look met. Independence means that we've independently selected them from each other. We didn't, but it did say they're random, they're representatives. That's good. Nearly normal. This does look to have a little, it's fine. It's pretty normal. Histogram looks pretty good. So we can do the view the histogram method of looking at it, and the histogram looks pretty good. All the assumptions, yeah, sure. Yeah, these are the not met ones. We're good. Random basically means independent and random. I just call it random. Sometimes my Pearson breaks it apart. Is 95 always going to be 2.01 like the Z? Depends on the degrees of freedom, Charlie. Depends on the degrees of freedom. The degrees of freedom change when you go to like a 95. If you have 30 degrees of freedom, it makes a different t-score. So when your degrees of freedom are different, your t-score will be different. So there won't always be a constant t-score for 95%. Does that make sense, Charlie? That what your t-score is will dictate. So you always have to know your degrees of freedom for your t, and then that will dictate what the 95% confidence t-score is. So always the degrees of freedom. Every t has degrees of freedom, and that tells you which t. Z-score is always 1.96. Z-score, there's no degrees of freedom. Z-score is always 1.96. Yeah, exactly. The more degrees of freedom you have, it'll go towards 1.96. The T basically becomes the normal with enough degrees of freedom. You can kind of watch as I give it more degrees of freedom, it turns into the normal, and it only achieves that with infinite degrees of freedom. More variability, exactly, with smaller sample sizes. You can see the more variability it gets. Mr. C says, I pay the fool, smashes it down. And yeah, that's excellent. Great review right there, Charlie. Yep, that's why you got to ask those questions. Once you review it a few times, really starts to make sense. It's like, okay, I got this. The T has more variability due to the uncertainty created due to smaller sample sizes. Oh, we're going to have to find, so we don't have the degrees of freedom. Degrees of freedom equals n minus 1. And n minus 1 is equal to 71. And so then we go S over square root of n. And so we have here y bar 23.7639 plus or minus. And we need to go get that t statistic. 71 degrees of freedom, go to the applet, put in our 71 degrees of freedom. If we're doing 95, we got the t statistic. We are doing 99. It's going to be even wider. So we need to go here. We'll put in 99 and go to the middle shading. 2.647. 2.647. This is where people usually get stuck. They can't get this t statistic. That's how you get it right there. 2.31 and standard deviation. Sample size. There we go. That's got the numbers. Let's go back to here. Let's solve it. So 72 square root 2.31517. There we go. Times that by 2.647. What did we just find? So we just found everything right there. We just found everything right there. We just found the margin of error. So that's usually where I pause when I'm solving these problems, not because of conditions, but I usually take a moment and write in, I think it was 0.7, right? Or let me double check. Yeah. And it's a bunch of 2s after that. 2, 2, 2, 2. Sure. 4 2s. Yeah, and that rounds down. Yep, 4 2s. Okay. So great job, Charlie, right there. 1,000 points. Excellent work today, Charlie. And this has got it now. That's, since we have the margin of error, we're just going to copy it. We're going to use that. And let's go here and start inputting the numbers. Okay, so not blocking it. Good. 23.7639 plus this. So that's 2 decimals. So 2449. And then 23.7639 minus that, 2304. And there we go. Got it. I am 99% confident that the true mean flight times, or the true mean proportion of flights that are delayed, is contained in the interval 23.04 to 24.49. There we go. And that's the true mean of monthly percentage flight delays. Make sure to do the context right there. That's got it. That's the quiz. So the homework, the quiz should be pretty similar. Charlie, are you working on any questions right now, Charlie? Let me know. Take a moment right here. See what people are thinking about the questions people are working on. Our goal is to do as many questions as we can, explain all the data. So we will see which questions are people working on. Which questions? I'm doing the hot dog one and missed part B, so I'm redoing it. Oh no! Yeah, it's so easy to make one of those mistakes, and that's some of the multiple choice are really. I hate that we don't know, and I'm glad it's in a video because. I mean, it's true. Yeah, we don't know, but I don't know. I wish they were more specific. I wish they just told you, because the we don't know. I guess they're trying to go real world, because sometimes you don't know. Forgot the conditions for a second. Condition 1, random. Condition 2, less than 10% or 10%, less than 10%. Condition 3, pause, nearly normal condition. So the third condition will be that it's nearly normal, and it just needs to look kind of unimodal and symmetric. With a sample size of 72, we meet the nearly normal condition because it doesn't have any heavy skew. If it had a heavy skew, we'd need at least 100 for a sample size. So we're doing excellent on that. Let's see if there's any others on the... Wait, Shakira, update. I got them now. Woo! Shakira, that's awesome. That is great work. Really proud of you right there. Great work. I'm so proud. It's some tricky problems. I knew you could do it. I knew you got it. It's... some people just... It's really sad. It's like, where's my sad music? Oh, we haven't played sad music in a while. People give up on the problems. People just give up. They say, I can't do this. Can't do it. Can't solve it. And it really bums me out. I'm like, no, you've got attempts. Especially the homework, you got infinite attempts. Give it a shot. Email me about what you're stuck on. A lot of times I'll send someone a video saying, like, here's kind of the video walkthrough, but then also I'll try to explain parts they're stuck on. We did that one. We did this one. So sometimes we'll be like, well, here's, the video help, and, tell me when you're stuck, because it's a little harder via email to figure out, but some people will like draw it out and then be like, here's what I worked. I'm like, oh, good, let's check over this. So this one right here, hoping to lure more shoppers downtown, a city builds a new parking garage in the central business district. The city plans to pay for the structure through parking fees. A random sample of 42 weekdays. That sounds like a sample size. Collected an average of 131. That sounds like a sample mean. With a standard deviation of 18, that sounds like a sample standard deviation. We've got a bunch of notation right here, so let's go grab that notation. I need to know your notation. I need to I stopped creating stuff to take a little more time to myself, but I want to be I want to make more stuff. I have to slow down sometimes. Slow down, Brian. Slow down. There's so much time. Winter break is coming up. Gotta make some plans on winter break. Got a bunch to do. Now this is Y bar because it's a sample mean. It's not mu because it's not the true mean. All of this information here comes from samples. And we can also go ahead and figure out the degrees of freedom for this. Degrees of freedom are n-1 for the one sample t, n-1. And that's going to make 41 degrees of freedom. And if it asks us for an interval, let's go find out if it asks for an interval, because I think it does. It wants a 95% confidence. So let's go grab the t statistic. So since we have 41 degrees of freedom and 95% confidence, I'll drop this in the chat here again. The t statistic is 2.02. So we've already got all of our notation for this problem. The t is a 2 points. Let's put the degrees of freedom on it. A t with 41 degrees of freedom is equal to 2.02. That's got it. That has it right here. And so we just start plugging in. We can actually kind of solve the interval. And s over square root of n. And square root of n. There we go. That's the interval. Once we solve it, we'll have the answer for the other part. Let's look at the other parts of the question. What assumptions must be made? We do not want at least 10%. That would violate the condition. The distribution is unimodal and symmetric with no outliers, no extreme. The data are randomly sampled, and we don't want them to be dependent. We want them to be independent. We want less than 10%. These are the reverse of the conditions. So we've got here our three conditions of random, 10%, and nearly normal. But they're tricking us by doing the 10% in the reverse. And then this is basically another way to say they're random. They're independent, but we don't want them to be dependent. If they're dependent, it'd not be random. Here's our interval right here. So we got to calculate it now. We actually have to do the work. Oh, man. So let's go here and calculate the interval. I always solve for the margin of error first. Type in your sample size, square root it. 18 divided by that, and times it by 2.02. 5.61 plus or minus 5.61, and then 131. So that's got that right there. And 131 plus. So the 10% condition is the 10% condition is its own thing. Independence is another way of saying random. So independence is another way of saying random, just to say they are like independent of each other. It means that they would have no connection. They're completely random of each other. So they're random and independent. I might try to mention that today in class. To be like, you can also say that they're independent. Which kind of, random includes independent. That's why I always have a gripe with that. Because it's like, you're also just basically saying, does that make sense, Charlie? Random would mean that they are independent. I am 95% confident that the true, we'll look at this in a second. S is standard deviation. S and it's sample standard deviation. Yep. So S equals sample standard. Let me write it down for you right here. Yeah, they break it apart. They break it into two parts, which I've never really liked because we even used the book for this course, and they break it into two parts because if it's random, it should be independent, because things that are dependent would not be random. So I've always had a problem because random encompasses independence. So does that make sense, Charlie? If it's random, it would be independent. And so, but they're also just including it's independent, which if it's random, it would be independent. They would not, because if it's dependent, it's not random. And so S is sample standard deviation and sigma is population standard deviation. So S is sample standard deviation and sigma is population standard deviation. Just like Y bar is sample mean and mu is population mean. Small differences right here. And it should be independent and random. They just break into two parts. They like doing that. It's how they do the problems. It's like, why? So what are we trying to estimate? I am 95% confident that the mean fall in the interval. No, please don't tell me that's the right answer. I am 95% confident the interval contains the mean daily income. So this looks correct right here. Let me double check. I am 95% confident that the interval contains the mean daily income. The confidence interval, there is 95% confidence that the daily income for a weekday. No, that doesn't even talk about the mean. So this one right here does not even mention the mean. That's wrong. 95% confidence that the mean daily income will fall. We don't like the word fall in statistics unless they're trying to trick me. Don't do that, my Pearson. It's saying that the truth will fall in the interval. No, the interval might contain the truth. There's 95% confidence that the daily income for all weekdays falls in the interval. So they've got another falls right there. So falls is a bad word. It's kind of saying this. Let me explain. Say, Brian, why do you keep saying falls is a bad word? If we have an interval right here, and we can create an interval, our interval might contain the truth. It's a horrible truth right there. Our interval might contain the truth. The truth doesn't fall inside our interval. Fall is an active word on the truth. Our interval might contain the truth. When we create an interval, it might contain the truth in it. The truth doesn't somehow jump inside of our interval. The fall has always been considered an active word on the truth, where our interval containing the truth is an active word on the interval. We create the interval, so the interval might be created and contain the truth. The truth does not fall inside the interval. Watch me be wrong. Explain what 95% confidence means. 95% of random samples will produce intervals that contain the truth 95% of the time. So 95% of samples of size 42 will produce intervals that contain the mean daily income. Yeah. The intervals might contain it 95% of the time. The consultant who advised the city on this project predicted that the parking avenues would make 127. Based on our interval, do we think this is possible? Do you think, Charlie, 127 is possible? Do you think? Let me see what Charlie said the other one. So what would a question look like if we had to choose which one to solve? Like if we have the... Yeah, that'd be hard. There's different ways to ask it. We asked one... Yeah, and this is believable. I think you're asking that. Let me answer those questions right there. So since the 95% confidence interval contains it, it is plausible. Got it. So those are hard questions to ask that we have to, when we differentiate stuff, but we could ask, there was a question on the second test that said something like, P is used in the interval to estimate the true proportion. No, P is the true proportion. So it says something like the true proportion is used in an interval to estimate the true proportion. And that would be false because you'd use the sample proportion. We use P hat plus or minus, margin of error. And just like we use Y hat plus or minus a margin of error, or excuse me, Y bar. So we use Y bar. You okay, computer? We use Y bar right here, which is the sample mean. And so we could do another question like that, like mu is used to estimate the true mean. No, mu is the true mean. So there's different ways to ask it. So a sample question could be, mu is used to estimate the true mean, and that'd be false. Y bar is used to estimate the true mean. And so I'm making all kinds of errors today. There we go right there. Let's knock out a few more questions right here. Let's do it. Where did all these? We did these. Oh, cool. I love these ones. I love these ones because you can guess them. So with this, let's take some guesses right here. You ready, Charlie? These are guesses. I should put up a warning. These are guesses. So a 90% confidence interval has a z-score of 1.645. So I'm going to go here and go 1.81 for this one. And 98 has a z-score of 2.3263. So I'm going to go 2.52. Am I right? 0. It's a bummer. Let's see how to solve these. 22 degrees of freedom, 90% confidence. So 22 degrees of freedom, 90% confidence, 1.717. Pretty off on that one. 98% confidence, 49 degrees of freedom. So we just change it to 49 degrees of freedom and 98% confidence, 2.405. Wow, really off. That was some of my worst guesses right there. Let's try one more similar question. Oh, we can't even do a similar question? I think if we recycle it, unless it just gives us the same one again. Okay, good, it didn't. So, if you know how the degrees of freedom work, I think I can get this one, Charlie, because this is going to be 2.60. 95% confidence is a z-score of what? What is the z-score for 95% confidence? The z-score. What is the z-score for 95% confidence? And I'll tell you how I guess it. The z-score for 95% confidence is going to be what? What is the classic z-score for 95% confidence? 1.96. So remember, the t-score is going to be more pressed out. So I'm going to take the z and just press it out a little bit more. It needs a pretty good press out because that's a lot lower. We got a 50. I think this one's the one that's wrong. There, we got it. 2 tries, we got it, Charlie. Because all I did was take my z and just press it out a little bit more. I also know the z-score for this one. This one's 2.57. So I went a little bit further out. Does that make sense, Charlie? The t-score is always a little bit further out. So here, we'll try another one right here. I was really disappointed in my first attempt. Okay, so Charlie, What do you guess for this one right here? What do you guess for this one? What do you guess for this one? Remember, it's gonna be more pushed out. You just gotta get really good at it. This one's the tough one. This one up here is the tough one, even though we know 1.96. And I think the last one was like 2.07. So, well, the last one was 2.07, and this one has less freedom. The last one was 2.07, and this one has less freedom. Do you get it? So this one, we already know 2.07 for like 25 degrees of freedom. This one has less freedom. So since this has less freedom to be normal, what do you guess for this one? So it has less freedom. Oh wait, but if that's more freedom will bring it back in towards the Z. Less freedom will push it out. So the less freedom it has, the further out it is, and this has less freedom. It'll be further out. So give me one more guess here. Give me one more guess. With less freedom, what would you go with? Because this has less freedom than the last one. I'm going to go with 2.12. It's got a considerable bit less freedom. We're going to go there. So this one, I know the Z score is 2.5758. This one has tons of degrees of freedom. Oh, yeah, no. Awesome. Yeah, good to see you, Rocky Top. Yeah, no, I was getting some stuff done, meeting with students and all that good stuff. Did some meetings, talked about tests today, and I'll go answer all the Discord stuff. But yeah, ask questions. We worked through a lot of the assignments already. This one right here, Charlie, what do you think? If the Z score is 2.5758 and we have tons of degrees of freedom, like we have a ton of degree of freedom, what do you think the T statistic will be? With tons of degrees of freedom, the Z and the T are basically identical because we have almost 100 degrees of freedom, which is a lot. After 60, it's virtually identical. So it's 2.57 with the Z for 99 because I have that one memorized. So the T might be what for this? I bet you can get this one because this one has a ton of degrees of freedom. This one has tons of degrees of freedom. I'd go with 2.59 because it's going to be very, very similar. The more degrees of freedom, we only got one. We only got one of these. There we go. Wow. There we go. Yeah, exactly. So we'll do one more. We'll do one more shot at these, and we'll go to the next one. I just have fun with these. Okay. So which of these is going to be more similar to the Z? The one with 12 degrees of freedom or 71? Which of these is going to be more similar to the Z? Which of these is going to be more similar to the Z? 71. The Z score for this is, I'll tell you the Z score. The Z score is 2.3263. So what do you think the T for this will be? This one's going to be more similar. But remember, the T is always further out. So this one's going to be more similar. What do you think it's going to be? I've got a range. I'm going to take your answers, Charlie. That's close. It's going to be close, I think. What was the last one? Maybe that's right. Maybe I shouldn't say anything. Maybe you're right, Charlie. I should not second guess Charlie. Never second guess Charlie. This one's the tough one. The Z score for this is that's the Z score. So what do you think this one is? This one's the tough one because this one has very little degrees of freedom, which means it's going to be very different. This one's the tough one because it's a lot more different. So there's a greater range of numbers. Because there's very little degrees of freedom, it's going to be a much more pushed out interval. It's going to be way different because there's very little degrees of freedom. So what do you think for this one? That's the Z score I've written in there right there. Because I have Z scores memorized because I use them so much. 90% confidence, 1.6449. Yeah. That's a really good guess, Charlie. That's really good. You might have got that one. Oh, no. I would go a little higher on that one. There we go. We got that one. You're probably right in the ballpark on this one. We might have to actually go look this one up because if it wants to the 100th, you're super close. Oh no, but you did really well. You were super close on that last one. And let's go look at this one. So people are wondering how you can actually do these. You'd put in 90% confidence with 12 degrees of freedom, 1.78. So 1.78. We'll do one more version of these really slowly. We're going to take our guesses to begin with, then we're going to check our answers. So 90% confidence with 25 degrees of freedom. We just saw an answer, so it's got to be closer in. So 1.72 and 98% confidence, very similar to the last one we did, 2.35. And now let's show the answers. 25 with 90 degrees of freedom. And I'll put this here in the chat again. 25 with 90 degrees of freedom is 1.71. So close. 98 with 72 degrees of freedom. 98 with 72 degrees of freedom. 98, 72 degrees of freedom, 2.38. Further off on that one, actually. And that should do it. We got it. So it's kind of a fun game to just guess them. I could, sit around. But does it make sense, Charlie? Like, you're getting a lot better at guessing them. And the more you kind of just mess around with this, the more you understand that when the degrees of freedom are really high, the numbers are super close. When the degrees of freedom are very small, the numbers are further out. You push out the numbers further. But good job on guessing those, but then always use the applet that we showed, and you can get the exact answers every time. So if you use the applets, you can always obtain the right answers. So here we are. We've got the same thing going on. 98% confidence with 6 degrees of freedom. Holy mackerel. I meant T is basically the Z. That's exactly it. Stat person is going to bust in the door and get mad at me. This one right here, I can guess 1.66. That's going to be that one. And I'll show that one. 103, 90% confidence interval. 103, 90% confidence interval. Boom. To the decimal. 1.66. Got that one. But the hard one is the other one. The hard one is going to be this 98 with 6. I don't even know. That's a really tough one. So little degrees of freedom is going to be really pushed out. And you can even see 3.14. I know that's a very small sample size. And you notice how it's really pushed out. With smaller degrees of freedom, the intervals get even more pushed out. So you can see as it gets more degrees of freedom, the interval starts to come in. Less degrees of freedom, the interval gets pushed out. So it's really hard to tell. And this is why I know the Z-score for a 98% confidence interval is 2.5758. So with enough degrees of freedom, you would see 2.5758 or 2.3263. Wow, I said the 99% confidence. I promise you I know them. That's the 99% confidence. 98 is 2.3263. And is it not 2.3263? I have to see something because it's rounding it differently. Q norm 2.3263. Why is their calculator rounding that to a 7? Do we not have enough confidence? I mean, not enough. We need to talk to these people. That's weird. It's 2.3263. I've seen that number for a long time. Confirming over here on R, it is 2.3263. These things matter. Okay, so that number right there is obtained. We're just having a little bit of fun right here. This is how I have fun. I think it was 98% confidence. So 98% confidence. And was it 6 degrees of freedom, Charlie? 6 degrees of freedom? 3.14. 3.14. So 3.14. That's got it. Excellent work. What if R is wrong? I highly doubt it. Here, we'll go to another site. Let me go to another site. So let's go to another site. And the other site, let's bring it over here. And the other site let's go to is Iowa Applet Normal. So this guy right here, Matt Bogner, he makes these really great applets too. And I'm going to make a 98% confidence interval and get the Z-score for it. And here is Matt Bogner's page. So that is Matt Bogner's number right there, 2.32635. And here is R, same numbers. You see it would round to 5 right there. So it looks like we've confirmed via 2 sites it is right. And I look up these numbers on tables a lot of times too. So 2.3263. So I was like, wait a minute. I have gotten a number wrong before. I used to think that a 68% confidence interval, which would be 16 on either side, I used to think that was 0. Oh my gosh, my brain's just breaking right now. So I used to think, no. If we have 68 in the middle, the in between 1 and -1, that's what I'm trying to say. So P norm. So I think you could make one of those using R. Yeah. Actually, that's the thing, Charlie. I have made one of these using R. I have made an applet. I might, if you want, I might go grab that. I've got the computer right here. If you want, Charlie, I could show you that because we're kind of, sometimes we have a little bit of fun. Do you want to see the applet I made, Charlie? Would you like to see that? I'll show you the applet I made right here, and you can tell me what you think about it. Do you want to see the applet I made using R? I'm going to assume yes. we've done a lot of the homework today, and so you made the table in Excel? Cool. Here, I'm still taking questions. I need to send this to myself. I want to put it on this computer, and for some reason, it searches all my emails on this computer now. I've still got Joker paint on this computer. Sorry, UT. But you can see the handprints from the Joker all over this computer. The clown makeup on the sides of it, because I was watching a video of the Joker and trying to do the Joker makeup to look more like the Joker. So so much fun. Oh, I might have found it. No. Where is it? It's on here. I need to find it. Enough from the clown. I think it was contingency table or something, but you made it and we used it for homework on Excel. Oh, no, you're talking about the regression solver, right? Are you talking about the regression solver, Charlie? Because I made a regression solver. My gosh, I hate the way it searches every email when I do a search. I'm not smart enough to know how to, and I'm trying to search Norm, and everything is looking up. Oh my gosh. I just want to find that folder. Kind. Sort by kind. I'll give a few shots at this. Does it put folders first? Where can I get a Switch? Probably. Really? That's such a bummer. That's a really good question. Nintendo Switch is awesome. You might have to go like eBay or something like that. Look on Amazon. Where I order online is going to be the best way, which just make sure you get a reputable site, because there are a lot of sites that I had the chance to order a PlayStation from a site that I was like, nope, not doing it. Not ordering from random sketchy site. Not going to do it. That is such a bummer. Where is it? Central limit theorem. Okay, I found something that helps. Good. I found my central limit theorem applet. What folder is this in? Where is this located? I hate file browsers. I've retried the quiz do so many times and it keeps giving me things wrong that are based on the. Can you send me a picture of it, Rocky Top? Can you send me a picture of it? Which one are you working on? Oh, no problem, Dan. We're still doing work right here. What do you have a question about, Dan? I'm trying to pull up an applet right here, and I don't know how to use a computer. Yeah, exactly. Yeah, that's exactly. There's so many sketchy sites that it's just not worth it. Where is this located on my... I hate Macs nowadays. Sorry, Macs. Get info. Where's this file located? B students. Oh, there we go. Here we go. What? Awesome. Oh, no. This is going to drive me mad right here. So this new section of chapter 14, is there anything new we need to know? Which one? The confidence rolls? Do you want to do one? If you have a problem, Dan, let me know. We'll hop in here. I'm trying to find this. Man. Wait. It keeps bringing me up my fonts when I type in normal. When I type in norm. I don't want norm. I want the folders. Oh, okay. Now we're on to something. I think I just found it. Found it. Okay, is that the latest one? Wow, it's that old. I should have never clicked off of it. 2 seconds, I think I found it. Oh, okay, then it's up here now because I just clicked it. Okay, wait, wrong one. Found it. Okay, cool. We grab these files, bring them over to here. So the confidence intervals for the mean. Yeah. Do you want to do one of those? I'm going to email this to myself. And we're going to get serious here. So I've actually been looking for this. Sure, which one do you want to do? Feel free to name it, and we will work the problem. So I'm going to pull up this file, these files right here, 2 seconds. This is the most interesting part of the class right here. Got one file attached to the email, and got the other file attached to the email, and just going to email it to myself, from myself, and call it norm. Send. Email has sent. We're good. Okay. Let's pull it up right here. Let's get the applet going up. Okay. Have it? Sure. Oh, cool. I don't have any of those lit. Okay, so let's go ahead and load this. Got it. Good. Does it run? And it looks like it's running. Cool. Let's load the other one. So all that work. What do we have now? All of this work. The question about the nutrition laboratory. Yeah, let's do this. Is it the hot dogs? We'll do it. You got it. So here we are, Charlie. I finally have it back. Here is the applet I created where you can put in your numbers and it'll draw on the curve for you. So this is all created inside of R right here. You can put in the mean. You can even put in your amount of decimals. Oh no, this isn't the updated one. I need to go in and update it again. But you can go ahead and put in whatever mean you want. You can put in the standard deviation you want. And you can put in the area on the curve. And I think, here we go, value from an area. And you can put in any area you want, and it'll draw it inside of R. So this is the applet, and we even uploaded it, but you can see all the code going on here that gets it to work inside of R. And I thought I had it where you could put in the decimals. There's the number of digits. Must have been when I was working on it, but I'm going to go look for this more now that I've almost found it on my computer. Let's do the nutrition laboratory question right here, which I don't think we've done on the, but just to show it could be done inside of R. But take a more look at it later. Here we go. Is this it? Here we go, Dan, right here. We got the nutrition laboratory question. 60 reduced sodium hot dogs found that the mean of them was 302 with a standard deviation of 37. So what do you notice for notation right here to start with? What notation do you see? What notation do you instantaneously see in this problem? Is there any notation that you're like, aha, I know what that is? What notation do you instantaneously see? We should see some notation right here that we are instantaneously like, I know what these things are. .302 is going to be the standard deviation of the sample. Oh, no, it's the mean, right? Oh, my gosh. This is why I don't know how to do these problems. And then you're right, it's the sample mean of the problem. And that's what Y bar stands for. We have the standard deviation. Nice job right there, Charlie and everybody. Great work. Teamwork. Awesome stuff. And then the degrees of freedom are going to be 59. Degrees of freedom for a one sample t is n minus 1. And so now we just need to find the t with 59 degrees of freedom for a 95% confidence. This is where people usually get stuck, but you need to go to the t applet, not this one. So here's the t applet. So we're going to go to a t with 59 degrees of freedom because n minus 1, 60 minus 1. And then we're going to put in here 95% confidence, and we're going to do the in-between. There we go. I don't know why it didn't look right. But this is a 95% confidence interval. The t is 2.001. So the t statistic is 2.001. From here, we're going to use the formula y bar, which is the sample mean, plus or minus our t statistic with n minus 1 degrees of freedom. That's subscript. We won't solve that. And then we do s over square root of n. Let's go ahead and plug in right here. We have the mean of 302. The standard deviation, or excuse me, the margin of error is going to be, do you have a command that... I just have it ready to go. Good question, Charlie. I should set up a bot when I'm like, we just use this site, and then it listens. Because I'll have a bot listen to me all day. That's not too Big Brother-esque, right? And there it is right there. There's the formula. So let's go ahead. I always like solving for the margin of error first. And the margin of error is going to be 60 square root and 37 divided by that times 2.001. And then we're just going to do 302 plus or minus 9.56. 302 plus or minus 9.56. And this right here is the margin of error. Just make sure you kind of understand how these formulas work when you're plugging in numbers. So the margin of error is the plus or minus. And let's do this. Oh, we should be able to do this in our head, right? So 302 plus 9.56, 311.56, 302, so 293.944. Let's double check. It's 302 minus 9.56. There's that right there. And oh, you see I did it wrong. There we go. There we go. And I think the other one's right. 302 plus this right here, 9.56. So we have the numbers correctly in the interval. What did we have to assume? We have to assume that the hot dogs' weights are normal. They're independent, which pretty much means they're random, but normal's kind of key right there for the nearly normal. Is the randomization condition met? We don't know. Only one decimal. Oh my gosh, Charlie. Charlie, you are the savior of the questions. Charlie, thank you so much. That'll get you. Please tell me if you get something wrong because of that. I will correct it because we all sometimes add one too many decimals. We don't know if the hot dogs were randomly sampled, but it's reasonable to think so. Are these less than 10% of all hot dogs? I certainly hope. We'll be running out of hot dogs if 60 hot dogs is not less than 10% of all hot dogs. So I'd say yes, 60 hot dogs is less than 10% of all hot dogs. Is the nearly normal condition satisfied? We don't know, but since the sample size is pretty large, kind of safe to think so, and so unless it's really skewed. What our interval means, I am 95% confident the true mean sodium content of the hot dogs is contained in the interval blank to blank, which sounds a lot like this, and we've done it. Does that make more sense, Dan? The rest of it's really just checking conditions, which are random, 10%, and nearly normal, because we're dealing with quantitative data. Very important to know that we're dealing with quantitative data. Quantitative? And that's got it right there. What other questions are there? Let's see, do we have any other? I think there's true, false, and stuff at the end, right? Suppose we are making a 95% confidence with a sample size of 15. What are the degrees of freedom? Is a one sample t or one sample t confidence interval? What are the degrees of freedom? So we're making a confidence interval for the mean, which is a one sample t interval. Awesome, Dan. So glad to hear that. And so this one's really easy. If you get this one, you're like, yes. Just boom. This one's really easy. Because we have 15 as our sample size, and then the degrees of freedom would be n minus 1. So the degrees of freedom for this are n minus 1. The complicated, super complex formula of n minus 1. So it'd be 14. Nice job right there, Dan. 1,000 points, Dan. Keep up the great work. It'd be n minus 1, so it's 14. Great job there. Going backwards now. Which of the following statements is true about the t distribution? It's symmetric and unimodal. Very true. You can see it right here. Let's go look at it. Unimodal and symmetric. Good, good, good. As the degrees of freedom increase, the t approaches the normal. Let's check that out. There's 1. There's 11. There's, look at that. As the degrees of freedom get larger, it goes towards the normal. So, yep, less degrees of freedom, less normal. More degrees of freedom, more normal. That is very true. T distributions have fatter tails and narrower centers. Let's look right here. If we give it very little degrees of freedom, fatter tails, narrower center, looks good to me. And as it goes up, approaches the normal, and the tails get skinnier, more normal. So we have confirmed that all of those are right answers. Just kind of some good notes to know about it. The golfer one, let's see here. Do we have any other super quick ones? Oh, this one, we should do this one. These use data. And hopefully people know how to solve these because we've been doing a few of these with the visualizations. But we have rats going through a maze. So we can take this data right here and we could work it by hand, or we could copy the data. So let's copy our data and let's bring the data over to Jump. And we're just going to open a new worksheet inside of Jump. And then we're going to go to Edit, Paste with Column Names. To open a new worksheet, go to New, Data Table, and then make sure you edit, paste with column names. Paste with column names. From here, we can go to Analyze Distribution like we did on our visualization. Double-click the variable. Click OK here. Stack it just to make it look nice. And we've done it. If it wants 95% confidence, we are good. But that's pretty far along. 90%. So we have to fix it. We have to go to the output. We have to go to the red arrow here, go to confidence interval, and change it to 90%. You've got all the options to change it. And now we have a 90% confidence interval up here. So let's see. We have right here the 90% confidence interval going from 47.66. So 47.66 all the way up to 57.60. 57.60. Are the conditions met for these data points? Well, let's look at the histogram. Which histogram does it look like? It looks like... So there's an outlier up there. If you notice, it's kind of got this peak and then the outlier. So it's got to be this one or this one. And it really looks a lot like this one. If you want to be certain, go here. And it goes from 20 to 100 in increments of 10. I think that's got it. And I think that's right. Or those are increments of 5, right? So I'm just double clicking the bottom bar. That's got it. Now it looks just like it. So what I'm doing is I'm double clicking this right here. And then I'm changing the min and the max and the increments. And I'm basing it off of the increments on the bottom here. Because we want it to look just like it. It's pretty much, you know, you've got this step right here. And they've got the outlier. So it's definitely this one right here. Definitely. The normal probability plot can only go up and to the right. But the thing is, on the left is the actual times, and here's the times of normal. Notice that there is a time up here around 100. There's a very extreme time of 92.7. And when you look down here, 92.7 is in this graphic, 92.7 is in this graphic, but this one's your perfect normal. This one does not have the 92.7. This one right here has the 92.7 when you trace over here. And the normal probability plot only goes up and to the right. So if you were to draw it, jump makes it look a little different, but you'll still see it goes up and to the right. And we have the point right there. It might be a little hard to see, but that's that point that doesn't follow it. And that's the point that doesn't follow it right there. For the majority, follows the normal, because this mostly follows the normal, and you have an outlier. Are the conditions satisfied? Everything's pretty much satisfied without the outlier. It's kind of the only issue. So let's look right here. With one outlier is what we need to say. Without the outlier, the conditions seem to be met. The histogram is roughly unimodal and symmetric with no outliers. Without the outlier, the conditions do not seem to be met. Okay, so that one's wrong. This one does not mention the outlier. This one's wrong. Without the outlier, the conditions seem to be met. The histogram is roughly bimodal. No. So it should be that, because the histogram is roughly unimodal and symmetric. This is bimodal, so that's wrong. And without the outlier, the conditions do not seem to be met. Probably if we remove the outlier. See, we remove it. You can't see my cursor's bigger on my screen for some reason. If we remove the outlier, it would probably be good. Eliminate the outlier and do the interval again. Now here's a trick. Here is the trick. The trick to this is as follows. Go here and go to redo auto recalc. Go here to the top arrow and go to redo auto recalc. And when you click on that, now go to your outlier and go up here. On a Mac, it'll be all the way at the top of the screen. But on a PC, it's this little bar you can't see. I want to show you again. You can't see this bar until you hover over it and then it appears. Go to rows with that row clicked. Make sure the row's clicked down here. Make sure that's clicked. And then go to hide and exclude. Now watch as the output changes because we have auto recalc on. If you have auto recalc on, it'll remove the outlier and auto recalc everything. So now we have the interval 46.85, 46.86. My gosh. 48.86. I think that's still wrong. Let me read it again. 46.86. My eyes are failing me. Not fun. 54.39. 54.39. There we go. As long as we're not making typos, we should be good. Does the maze meet the requirements that it takes at least a minute? Is 1 minute in the interval? Nope. So the maze does not meet the requirement. Does the other interval contain it? The other interval does not either. So both confidence intervals are entirely below it. It does not meet the 1 minute requirement. Both intervals are entirely below. We aced that question. A little bit tricky of a question. A lot of parts to it. Glad we did the rat in a maze question. But if you know how to use jump, it makes it a good bit easier. Jump can really help with those problems. This is another jump problem right here because we'll copy that data into jump. And this is another jump problem. We'll copy that data into jump. What are people working on? We know how to do this one. Hey, Brian, what's the name of the website where we find the degrees with the table with the degrees of freedom? It is... Gotta use... There you go. You want to do the yogurt one? Sure, let's do the yogurt one. You got it. But let's find the yogurt one. Must have just passed it. I think it was the laboratory one, right? That's the 1,000-chip trial? Here we go, yogurt. Okay, let's do the yogurt one. Okay. So we have data right here from yogurt, and it's how many calories, yogurt, something like that. We're going to take this data, we're going to copy it to the clipboard, and boom, we got it copied. With the data copied, now we're going to go over to Jump, and we're going to open up a new data table. So with Jump open, go to File, New, Data Table. That's key right there. We're going to go here and go to Edit, Paste with Column Names. If I can find it, there we go, Paste with Column Names. Up. We do not want to paste with column names because there is no column name. This is an error. The first number should not be in the column. So we're going to not use this. We're going to go to File, New Data Table, and now we're just going to go to Edit, Paste. Please note the difference right here, that now the first observation is in the first row. If there was a column name, we'd have to paste with column names. So make sure you go to Edit, Paste. This is the correct way for this problem. Problems have different ways of completing them, just depends on what data we're working with. This previous one did have a column name, so we had to paste with the column name. This one does not have a column name, so we just paste. So what does the question want us to do? Wants us to first look at the histogram. You can see there is like one low 96, which there's not a second mode down here, so this is kind of it's all by itself. And it goes up to 168, 165, so that eliminates this one right here and eliminates this one. The answer should be this one. Let's confirm by making the histogram right here. Analyze, distribution, double click, click OK. And it kind of looks like that one. So it kind of looks like the one I selected right here. It goes from 80 to 200 with jumps of 20. 80 to 200 with jumps of 20. If you double click the bottom of it, there we go. So once again, bin widths control the way it's shaped. So if you look at the 80 to 200, that's why I put 80 to 200 right here. Goes to 80 to 200. And then the bin widths are 20. This goes 80, 100. So I want mine to look just like it. If you double click, you can choose how it looks. I don't know why the 200 doesn't show up. That's why I decided to pull this out a tiny bit, just so you could see the 200 right there and see that we've done the same graphic right there. So that does confirm this is the right option. How does the normal quantile plot look? Normal quantile plots can only go up and to the right. There's a huge gap in the data right here. If you notice, there's a gap with a high outlier of 170, 60 something, but there's a 165 and 160. These are the numbers right here. You see these two numbers? That's the 165, that's the 168, and those are the numbers right there. If you trace over, that'd be 165 and 168, and they can only go up and to the right. So knowing this about normal probability plots, that if you make a normal probability plot here, normal quantile plot also known, it can only go up and to the right. The way that Jump presents it doesn't look exactly like the ones you create, but you can only pick from the ones that go up and to the right. So you're eliminating down to these two options. This one has one high point that if you look at it, let's go really big on it right here. We'll do this. There's one high point that's about 170 or so. But this one over here has two high points that are 165 and 167, I believe. And you see them right here. There's your two high observations, 165 and 168, and there they are right there. We should have two observations that are super close next to each other as the next two highest, and those are the 153 and 154. Those are the observations right here. You can see the lowest observation is about 94. The lowest observation is 96. So hopefully we can kind of do a process of elimination, but we can also use Jump to help us out. Once again, it can only go up and to the right, so that's the only option. Are the assumptions and conditions met? Random, sure. The normal probability plot is roughly straight and does not have extreme outliers. The histogram is not skewed, so that one's wrong. This one's wrong because the histogram is not skewed. This one's wrong because we have random right here. We're going to assume randomness because I wish my Pearson said it. The normal condition, random's good. Normal probability plot is straight and roughly symmetric. So the nearly normal condition is met. That sounds good to me. It's not bimodal histogram, not bimodal. Find a 95% confidence interval. Guess what? We've already done it. By doing this inside of Jump, it already did all the work for us, and we have 117.34. it's already computed it right over here on the side. There's the lower bound and here's the upper bound. And so there we go. A diet guide claimed that you will get an average of 140. Do we think this is possible? You look at your interval and you say, okay, I'm 95% confident the true mean content of yogurt from this brand is contained in the interval 117.34 to 150.11. So the confidence interval contains it. So the claim is supported by the confidence interval. And we did it. Another 100. Good stuff right there. It's so easy to make a little mistake. Sometimes I even get a little bit worried and I'm like double checking. I'm like, okay, did we enter the right decimals? 2 decimals. Please tell me if you get something wrong because of decimals. You know, especially if you enter too many. I'm always like, okay, obviously you knew it. I'll give you the points back because that's really not fair. What other questions are there? We've done, I think, mostly all of them today. We've done all the ones there with, so let's see here. We didn't do the 1,000 chip trial. So this one is very similar. This one, yeah, we'll do this one because it has a trick at the end. So this one is the 1,000 chip trial. And we hear from a company that each bag has 1,000 chips in it. So we want to see if on average, hint right there for the last part of this question, if on average the bags would have 1,000 chips in them. Let's go ahead and copy our data over. It does not look like it has a column name. So when we paste on our new data sheet, so we can go anywhere and go to File, New Data Table, we are just going to paste. We are not going to paste with column names. So we've just pasted here the data. So we can go ahead and analyze the distribution. Why not? Let's go ahead here, and there's the distribution. And let's go look at the question, and we've got the data already analyzed and ready to go. So check the assumptions. Did it say we got random bags? So this is good. The sample is less than 10%, so one can assume the data are from a random sample. So one can assume that they are not, so one can assume they are independent. That's exactly what I'm talking about right here, is if they're random, they're basically independent. Students purchase random bags. Okay, good. So when we check the independence, since they're from a random sample, you can assume independence. That's exactly what I was getting at. Once again, our histogram does not look like theirs due to bin widths. It does have a peak in the middle, so we're between these two. And look at this one, it goes all the way down to about 800 or so. This one starts at about 1,000, and you can see that's where it starts. That's going to be the answer. We can adjust our histogram to be 700 to 1,500. 700 to 1,500. Is that right? What are the increments? 9,000. That's so weird. Let's grab the... We can change this. Sure. There we go. There we go. Okay, cool. Just try to make it look like it, and you can see if we were to pull this out a little bit right here. There we go. So it looks most like this one. You can see. So just kind of, the bin widths here are a little bit weird. 1,000, 1, 11, 12, 13, 14, 15, 16. Yeah, their bin widths are a little bit odd. I don't know how they're getting that. It's the first one I've had that doesn't turn out exactly like it, and I don't like that. Evaluate the histogram. Oh, that's as unimodal and symmetric as it gets. That is extremely normal, so we definitely passed the nearly normal. So it's unimodal and symmetric with no outliers. So one can assume, and this one does not say the no outliers, so that's going to be very important. Ah, wait, there's a problem, though. They might have switched this semester. Do we know what is true about the family? Yep. We'll hop back to that in a second here, Charlie. Tell me what you think is true about it. And I'll evaluate, and then we'll hop back to that one. So we're going to use the t distribution right here. And so this one is a little bit of a trick. We are using the t. We are not using the normal. I'm a little worried about this one because I do like that this says no outliers, but I know we're using the t distribution. And we've already created the interval right here. So the interval is 1145.3. And the upper interval is 1338.9. And what does the evidence say about the company's claim? They claim 1,000 chips in each bag. Because the confidence interval is entirely above 1,000, the mean number of chips per bag is likely more than 1,000. That means that every bag contains at least 1,000. No. It means that the mean, on average, bags are expected to, because this bag almost didn't contain 1,000. So we're talking about estimating the mean. Because the confidence interval includes, it does not include. Because the confidence interval includes, does not include. So the answer has to be this one. Symmetric and unimodal as the t gets rid of the degrees of proportionality. I don't think they have. Yep. So here's what the does the t look to have fatter tails, Charlie? Here's the normal. Here's basically the normal. Here's the t. Does the t look to have fatter tails? Here's the normal. Here's the t. Here's the normal. Here's the t. Well, this is basically normal because here's the normal right here, and then here's a t with very little degrees of freedom, and here's the normal. Yep. The t is more narrow towards the center. It gets flattened out. It actually kind of gets squished in all directions. But the t is more narrow, has fatter tails compared to the normal. It's just when the t gets enough degrees of freedom, here's basically the normal, and here's the t with very few degrees of freedom, and here's basically the normal. So you can kind of see the t has fatter tails. Great question right there, Charlie. Great work. And the trick, what do we do? We went too quickly. Is it really this one? I knew it would be that one. I knew it. The t is an extension of the normal. I really have issues with that. We should mention that it has no outliers. I was thinking it would be that. I knew it. Not today, my Pearson. Man, we just got to play. It's like knock over my computer. Oh, man. Sad music when we get something wrong. So my qualms with this is that we should acknowledge there are no outliers, but we are using the t distribution for this. And so, but the t is an extension of the normal. So it's one of those ones when you get your test back that you argue with the teacher about it. You're like, I don't think I got this wrong. I don't think I got that question wrong. So we've basically done it. I think we're good. I think we are good. We'll check back tomorrow. And any other last questions, Charlie, Dan, anyone else? We've done a lot of work today. We've done a lot of problems. Oh, gotta get some water. Gonna get ready to teach. Hop on Discord, see how everyone's doing. You're welcome, Nicholas. Excellent work. We got some 320 done at the very start of this. I've been putting all the marks in the videos. Mubot is here. Great job, Nicholas. Nicholas, you're going to get to the gold tier by the end of the semester, I believe. That's awesome. We have less than 3 weeks of classes left. Less than 3 weeks. Independent is basically random. If it is random, you can assume independence. So we kind of bundle them together that random basically implies independence. So if it's random, they should be independent. Because if they're not random, if they are not random, they might not be independent. But I basically join them together. Does that make sense, Charlie? If you're working on what about the plan question real quick? What's the plan question? Is it a plane or the plan? Which one is it? The plan question? Which one's the plan question? Can you copy a little bit more of it for me, and I will figure it out. The plan. Flight question, sorry. Okay, the plane. I thought it was plane. I was like, I don't remember a plan question. Oh, no, we broke my Pearson. No, we didn't break it. Psychology on rats. Oh, but the flight's leaving on time? Yep. I think we did that one earlier. So the flight's leaving on time. Where is it? Here we go, right here. This one, we did this one in the homework earlier. So independence is basically random. So it should be met right there. Exactly. You're so close to the golds here. You guys got this. And so are the independence conditions met? Independence condition would be met because we're selecting random flights. Is the randomization condition met, or is sample suitable representative? Yes. Be very careful to switch the yes and no's. This is less than 10% of all flights. Is it nearly normal? Yes. Yep. Looks good. 90% confidence. So you know what? We should be able to solve this really quickly. Let's do this. Watch this. We've already got our cheat sheet up right here. The mean is 80. Can I copy? No. 80.0972. 80.0972. The standard deviation is 2.66646. And we need the t-statistic. The t-statistic is going to be for a 90%. And the degrees of freedom related to the sample size. The sample size is 72. And I think that's done it. Hopefully I didn't go too quickly, but 79.91. So 79.91 and 80.28. Interpret the interval. We are 90% confident that the true mean monthly percentage of on-time departures is contained in the interval. Oh my gosh, what did we do wrong right here? I think it's our interval, right? Did I not put in the right numbers? Let's see right here. Oh, my gosh, what am I doing? The degrees of freedom, or the sample size, I knocked a key over. 79.57. I cannot type numbers. And 80.62. There we go. I hate that my Pearson does that on the test. We'll definitely say it's random. So if my Pearson doesn't say it's not random, then either assume it or say yes. If it says like we would assume, yeah. So some of these questions are a little tricky on the randomness, but usually you just assume unless they don't say it's unless they say explicitly it's not random. Unless they explicitly say it's not random. And we have our solver over here if I know how to type the numbers in the right way. So unless they explicitly say it's not random, so usually just assume randomness for the Pearson problems. We'll say it on the test, though. We'll make it very clear on the test that we took a random sample of students, or we took a random sample of hot dogs, or we took a random sample of flights. We'll make that very, very clear. So hopefully it doesn't cause any confusion. So we will definitely let you know it's a random sample. We should go in and edit my Pearson questions. Be like random or not random. I think that's got it. Does this make sense, Charlie, right here? Our solver failed us. We don't know how to type in numbers. How did I get that 5 in there? Did I not delete the previous number? But I had the wrong, so I had the wrong N and I had the wrong degrees of freedom and I had the wrong T statistic because I calculated my degrees of freedom from my T. And then I solve right here for the margin of error. And then I do plus or minus the margin of error. Yeah, I don't like that. I think they're trying to be like brevity's sake. And then I don't like that they don't explicitly say it's random or not random, because they really need to be like, this is random or this was not random. We took a random sample that was randomly collected. They could just simply say random. And I think it's just some people write the questions who don't realize that they really need to make that clear. And then maybe someone's like, well, I guess we'll say we could assume. And yeah, I think it should be kind of clear. Yeah, no, I think it's got it. I'm gonna knock things over. Well, great job, Charlie. Great job, Dan. Great job, Nicholas. Great job. I think Jessica was here too. Rocky Top Stats. So good seeing everybody. I will be back. We're going to be teaching hypothesis testing later today. So stay tuned. And remember, we'll put some marks in this video if you want to come back, working on the homework and quiz for tomorrow. But that's got it. I will see everybody later. Bye for now.